Hello, folks. Welcome back. Happy Monday. First things first, we do have an audit schedule today. The week is off, right? Because Thursday you guys get a holiday. Veterans Day, no school. So they took out the first through fourth period that was supposed to be on Thursday, and they moved it to today. So today is first through fourth period. But because you guys are used to getting out Mondays at 2:50, they shortened things up, so it's closer to that. Tuesdays are longer periods. So it's 10 minutes off each period. Today our class is 10:05 to 11:25. First things, the test. We started that on Thursday. Hopefully you guys have had a chance to get at least one of those rounds done. Again, as we talked about before, the test must be done in class with me. So if you didn't finish your 3 efforts or your tries you needed to do to get your strong score, you can do it for a second or third try today. If we have some work session after the instruction, you can do it now, or tomorrow after the instruction, you can do it then, or Wednesday, you can do it during tutorial, or Friday during tutorial. Please note that grades are due for me for the R2 grading period tomorrow. That means if you choose to wait until Wednesday to finish it up, that's okay. It'll eventually catch up, but your progress report would show the grade that you've earned to this as well. Any questions on that? Okay. Today I'm going to teach you some high-level stuff just to get your perspective, and then we'll do some very discrete skills that will get you where you need to go for today's homework. I want to start by talking about the center. So this is a circle. How would you define the center of a circle? Christian?
A point that's like equidistant from all spots on the edge.
Perfect. Remember that a circle has this radius in its unique. The radius is the same no matter what direction you go, which means that it is the point that is the same distance from each side. Right? So what if I ask you to tell me what the center of a square is? Could you use the same definition? Could you say it's the point that is equidistant from all points on the square? No, because this corner.
You need all sides.
You could say we're all sides of the same distance because we talked about the distance from a point to a segment is going to be perpendicular. So isn't it the same distance from all sides?
What's the center of all sides? Because what if you did it like over the corner?
Right, but we don't want to use the word center in defining center, do we? That's circular logic.
Yeah.
I swear. So we're going to say that it's the point that's equidistant from all sides, but could you also have said it's equidistant from all vertices? Sure, in a square that works. What if I asked you to find the center of a triangle? What would that mean? Question?
Vertices.
Equidistant from all vertices. Would you agree that would find the center? Could you again also say that it's equidistant from all the sides? That would also work. Now, what's weird about triangles is if we are looking at this triangle, an equilateral triangle, all 3 sides the same, then those 2 points fall in the same spot. But if I were to pick a non-regular triangle, now what's equidistant from these 3 corners would be a spot there. Actually, no, it's going to be over there. Whereas what's equidistant from the sides would be there. They're different centers.
Couldn't you go from one like vertice to the midpoint of
The side?
on the other side?
Sure. Hold that thought there, right? So you guys ever go to Ghirardelli Square? It's in San Francisco, and they make chocolate, right? When I was a kid, I think they were a little bit freer with the ways in which they care about food preparation. So they used to take us in there and give us a little Dixie cup, and we could scoop it out of the vat to get a cup full of chocolate. Like Willy Wonka, right? It was amazing. I don't think they do that anymore, but I think you can go there and you can buy like a broken off chunk of chocolate, and they just sell it to you by weight. Now let's say you went there with a buddy. and you guys wanted to share this. How could you split some random triangle into 2 equal parts? Take a moment, talk to your neighbors, and come up with how you can split a piece of triangular chocolate into 2 equal parts. Go. Okay, Jonathan's getting all kinds of creative. He's melting the chocolate down. Very creative. But what I'm going towards is, how can we take a triangle and cut it in half? Don't go melting.
No, I
triangles in half.
actually have a thing.
Okay.
But like you could segment it into smaller shapes. And then,
Okay, how many? Are you talking like a bunch?
yeah. And then
Okay.
you like put those shapes in half, right? Or you could do it by weight, I guess.
Okay, but let's say that you broke it down into triangles and then you cut those in half. My point is, how do you cut a triangle in half?
You don't.
Josh?
Where you go from like the smallest, or like the verse with like the smallest angle, so like on the very right,
Okay,
and then you cut it kind of like straight out into like,
into this space.
yeah. like a
So-
certain angle.
At a certain angle, that's what I want to get at though. What is that certain angle? How do we know how to do that? Would you agree that one way to think about it would be to perfectly split this angle in half?
Yeah, but then the guy on the
Does
top.
that feel like it kind of splits it? But is there another way you could do it where you go from here to explicitly the midpoint of this side? Does that also kind of split it in half?
Yeah.
Now, turns out that in triangles, there are actually 4 different centers. What? I said there's 4, no, there's 4 different centers. And that's what we're gonna do next class. So please, 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 next class, bring your compass. This next class, we're gonna find all those centers. But today, to prepare you for that, we have to talk about what it means to cut across a triangle. How are the different ways we could draw a segment that kind of splits a triangle in half? This is not in your notes. This is just for you to sit back and take in as intelligence. We've got 4 different ways we can split a triangle, quote unquote, in half. One of them is a perpendicular bisect. As in geometry, normally, the words tell us what to do. What does a bisector mean? Nice and loud, we're being recorded.
We are? We are.
Well, you're not.
Oh, I'm not goes to the midpoint.
Midpoint, key, right? So if I take this side, for example, and I find whatever the midpoint is, showing that these 2 segments are the same, and then I need to go perpendicular from that. So that means I'm going through that point straight up in a way that's perpendicular. Does it go through the vertex and cut that triangle in half?
No.
No, that's unsatisfying as a slice through the middle of the triangle, isn't
The
it?
guy on the right is gonna get like more chocolate, right?
I think you're right. But let's see. What about an angle bisector? What does that mean? Agree?
It is the triangle up there, it's half of the degree of the angle.
Yes, I look at however big this angle is and I say I'm going to split it exactly in half.
Well,
And might that go through the midpoint here?
yeah.
Good. Might it also not go through the midpoint? But will it definitely go through the vertex? Yes.
This is kind of random, but like, if the chocolate is a raised piece,
Yes.
instead of 3-dimensional, you could slice it through the center.
You're right. But chocolate isn't. It's got those little lumps and then.
Oh, yeah, that's true.
Yeah, that's like that whole, how do you split a cake in half perfectly? And they say, yeah, just slice it this way. But come on, the top of the cake is not the same as the bottom. Same. Now we're all hungry. What about a median? You guys ever heard the phrase median? What is it? Middle, right? Like when you're driving down the road, there's a median that's in the middle.
That's called median?
It is. There's also an average. A median is a type of middle. So if we're talking about the median of a triangle, it's where you go from that midpoint again, but now you go to the opposite vertex.
I still feel like you're down the right signal, Chuck.
Do you? No, you think it's the same?
Yeah.
Why? Explain.
Because I think combining the two, you combine the angle size and the perpendicular bisector, and it creates even both sides.
Okay, all right. Not sure I'm convinced by your argument, but I like your solution. These are the same size.
That's bogus.
Let me prove it to you.
That's an optical illusion.
Do you agree that we're talking about a two-dimensional shape here? There's no thickness in this one. So what we're comparing is the area of this shape and the area of this shape. Agreed?
Oh, I get it, never mind.
I'm gonna say it anyway, just in case somebody.
Yeah, okay.
How do you find the area of a triangle? What?
You start finding out what to.
Area equals 1/2 base times height. Good. And what has to be true about the base and the height when you're using this idea?
They're the same.
No.
Well, yeah, they're the same base.
Yeah, but I mean, base and height. In a triangle, when I'm finding the area of a triangle, like let's say that I've got a right triangle like this, 3, 4, and 5. Can I use 5 as the base?
No.
Sure I can, but what would the height be? We can't see it.
Yeah.
I need the height to be perpendicular. It can't be 3 because those are not perpendicular to each other. So the area of this one, I'd have to twist it around and say that the base is 3, the height is 4, 1/2, 3 times 4 is 6. The area of the shape is 6. I could use the 4 as the base. 4 times 3 is 12, divided by 2 is 6. It's still the same area. But if I wanted to use the 5, I'd need to find out what this height is, what's perpendicular to the 5. It always has to be perpendicular. So when I'm talking about the area of this shape, this one is going to be this base times whatever that altitude is, the height. And this one's going to be this base times whatever that same altitude is. In other words, they both got the same length of base, and they both got the same altitude. So when you do 1/2 base times height, they're going to be the same area. The median does split into two equal areas. Are these two shapes congruent? No. They're different shapes triangles. This one's an obtuse triangle. This one's an acute triangle. Congruence is not the same as equal. We've talked about that. But if we're just talking about chocolate, we don't care which one has bigger angles. We care about getting equal volume to make our stomachs just as sick, right? Okay, what about this last one? What's an altitude? What does that look like? Remember? The height, right? And we just talked about that. So let's say you're standing out on this mountaintop and you want to measure how high you are in the air. You might take a string, put a rock on the bottom and lower it down.
You would?
That's what I do.
That's all. Okay.
Yeah, what would you do?
I don't
Take
know.
out your phone and say, what's my height? Say you're stuck on a
I
desert.
don't know, it
island.
just feels like that's just a lot of string.
Don't you bring string when you hike? I bring a lot. Anyway, so what we're talking about is it has to be a line that goes from the apex, the vertex, perpendicular to the base, and it may or may not hit the midpoint of that base. These are 4 different ways we can slice a triangle into quote unquote half.
I drill a hole down the peak and then I drop a.
Sorry, so you don't bring the string, but you bring a granite boring drill. Want to go hiking with you, that's for sure. Okay. So let's take a look at what these things have in common and what they've got for different. Do they all go through the vertex? Which ones go through the vertex? Do we agree the altitude goes through the vertex every single time?
Yes.
100%. Does the median go through the vertex every single time? 100%. Does the angle bisector go through the vertex?
Yes.
Does the perpendicular bisector go through the vertex?
No.
No, it could. Turns out it's for isosceles triangles and equilateral, but not all times. Second one, is it perpendicular to the base? In a perpendicular bisector, is it perpendicular? Yeah, it's in the name. Is an angle bisector perpendicular to the base?
No.
Not necessarily, good answer. Is a median perpendicular to the base? That's not this one, this was our area discussion. No, it's not. Is an altitude perpendicular to the base? It is. Does it contain the midpoint of the side? Perpendicular bisector?
Yes,
Yeah, bisector, that's what it means. Does
Yeah.
the angle bisector contain the midpoint?
yes.
Not necessarily.
No, it goes through here. I know you haven't seen enough of these to know for sure, but there's no reason to say that it's gonna go here or here or here.
Looks
It's all based on this angle.
Oh,
What about the median?
yeah.
Yeah, that's what it says. It goes through the midpoint and through the vertex. So of course it goes through the midpoint. What about the altitude? No, because we could have a triangle that's like this, where the altitude is way over here. It's not going through the midpoint. Last one, does it bisect the vertex angle? Does the perpendicular bisector bisect the vertex angle? No, it doesn't go through the vertex, does it? Does the angle bisector bisect the angle? Yes.
Sure.
Does the median bisect the angle?
Yes.
No.
No, it doesn't, because if it
Well,
did,
it can, but.
it can, but it doesn't have to. What about the altitude?
No.
Yeah.
Again, it doesn't have to. So step back and look at our chart. What do you notice?
It has a pattern.
It does have a pattern. What's the pattern?
Circular patterns.
What is the pattern?
A circle.
Look, you know, I'm good at patterns, but I see triangles, I see rectangles, I see check marks. I don't see any circles.
Well, yeah, see the checks more
Yeah.
like a circle. Like
Okay,
a.
we'll talk more about circles later. Yeah, right. Say again?
They only have two.
They only have two. Every type of segment that cuts through a triangle has two features. This one is perpendicular and through the midpoint. This one is through the vertex and the angle bisector. This one's through the vertex and through the midpoint. This one's through the vertex and it's perpendicular. Tomorrow, you're going to be expected to be able to look at a shape with a mark on it to show what these segments are and determine, is this an angle bisector, is this an altitude, right? That's where we're going. Today, we're going to be focused on the fifth one. Question?
So all of these are in the middle of it. Are we trying, so for this, we're trying to split it evenly. We're going to do the middle, which you do it on all sides.
It turns out if you did perpendicular bisectors from all three sides, that would form a particular middle that we'll talk about in just a moment. If you were to do an angle bisector from all three angles, that would give you a different center that has a different feature to it. If you were to do a median from all three sides, it would give you a third section, a third center.
So what's the real center?
Oh, these four.
Those four at the end. And we'll get there in just a second to do those notes.
Oh,
Yes.
so what's the real center?
I don't know.
What?
What do you mean? It depends on your need.
Oh. Well,
Give me about 4 minutes and I'll get you to describe all the centers in the city. They each have something significant.
okay. I guess
I love your intellectual curiosity. You want to get there and I'm going to give you that. I'll
it's
satisfy
just
that.
kind of
Give me a minute.
in my mind, like how can you have 4 trees? You know?
Well, the question is what the word center means. Do you agree that I could take a triangle and make it equidistant from all 4 sides, and that might be considered a center?
Sure, but it doesn't look like it.
No, it doesn't. But it would draw a circle that perfectly sits in the middle. That's supposed to be what's inside there. That feels like a center. I could also take one that is the center of all 3 vertices. It's the same distance from all 3 vertices.
Okay.
And that's kind of the center as well, even though that actually can fall outside of the triangle to make matters really confusing. And then lastly, you ever seen guys like, or girls or non-binary, take an object and spin it? Random things.
It's like a basketball.
Basketballs are easy. Some people do plates, some people do chairs, small animals, whatever it is, you're spinning these things, right? But in order to spin it, you have to have this center of gravity. So if you were spinning a triangle, how would you find that center? Do you agree that that center is different and important?
Well, you wouldn't be spinning a triangle because you can't.
Because you
have
got
a
the granite more and
two-dimensional
drill.
object.
Hands are full.
You can't have a two-dimensional object.
You could have, I mean, as long as it's the same thickness all the way through, like a piece of plate or a platter or something like that, or a nice cut of wood that's a charcuterie board that's triangular.
Oh, yeah, yeah.
Only marin. So turns out if I take the median from all three sides, remember we talked about that being the midpoint to the opposite, all three of those will meet at some point, and that's the perfect center of gravity. If you were going to spin stuff, that's where you'd spin. It's different than these two centers, but it's another center. We'll get there in just a minute. Give me another moment. Okay. There's a fifth way that we can slice through a triangle. This is called a mid-segment, and as always in geometry, we really try to make the words tell you what the object is. So what's a mid-segment?
We like find the middle of each segment, just put a line through it.
Excellent. If I take the midpoint of this side, and then I take the midpoint of this side, they're different lengths. So of course, these marks say these are the same. These marks say these are the same, but these aren't the same. And if I connect them, that's a segment connecting midpoints. Well, what if I did the same thing over here? It makes a tiny little triangle. And is that tiny little triangle significant?
It has half on it.
Yes, take that a little bit further.
Oh, it's
Another
so
score.
If this is 3, and this is 3, I don't know what that stands for, but these 3 hash marks mean the same.
that one, the blue one, is also.
And if this has 2 and this has 2, the green one's 2. And if this has 1 and this has 1. So what's true about all 4 of these triangles? Better than equal, they are congruent. All 4 of these triangles have the same length sides. And triangles are unique this way. Like if I take 3 sticks and I put them together to make a triangle, and then I ask Leo to take the same 3-sided sticks and put them together to make a triangle, will he make a triangle that's the same as mine? Yes. But if we each worked with 4 sticks to create a quadrilateral, he can make his narrower or wider. He can connect different parts or it would be a totally different shape. But triangles are unique. If I give you the 3 same size sticks, those triangles will always be the same. We just skipped a unit, chapter 5, that talked all about congruent triangles. We'll bring that back in the spring. But conceptually, if I take this image and I dilate it, just learned about doubling this side and doubling this side. Wouldn't this side also double? So this side will be the same as half of this side. And if these triangles are the same, they're congruent. What's true about these 2 angles? They have to be the same, don't they? The angle between the mark of 2 and the mark of 3 has to be the same as the angle between the mark 2 and the mark of 3 if those triangles are congruent. And if this is like a transversal, cutting through those 2 lines, and these 2 angles are the same, what kind of angles are they? Corresponding angles. If corresponding angles are congruent, what's true about these 2 orange lines? They're parallel. Okay. I mean, something in the world makes sense. I came in confused. Okay. So
Where's the middle?
and I left confused. All right.
Oh, well, what's the point of that?
There is middle. I will show you. All right, let's go to our notes and give it some structure here. By the way, you guys make an excellent TV audience. Okay. So here's our notes for the day. Oh, that's going to be really frustrating. It's possible that I may or may not have not shared that entire thing when I was recording it. Okay, we're going to start with a mid-segment. This is the last one we just talked about. A mid-segment joins the blanks of 2 sides of a triangle. Midpoints. And again, that means that we're creating a midpoint here and a midpoint there. And we're connecting those. That is a midsegment. We'll talk on the next page about the features and attributes. This page is just about identifying them. Next, we'll talk about a perpendicular bisector. It's a line segment array that divides a segment into two equal. Remember, because it's a bisector. So we expect it to go through the midpoint. And it's what to the segment? Perpendicular. Now, I'm going to specifically lean this when I draw it to show that it doesn't go through B. Because they drew this as kind of an equilateral triangle or an isosceles anyway. So it looks like it should go through B, but perpendicular bisectors don't always. Third one is an angle bisector. A line segment array that divides an angle into two, good, equal parts. The angle has been bisected. And then a median is a segment that connects a yes, but the way they phrase this, it's a vertex of a triangle to the midpoint of the opposite side. So it's connecting the midpoint to the vertex. And then an altitude connects a vertex of a triangle to the opposite side so that it is perpendicular to that side. And it doesn't have to be through the midpoint. It could. Now, once again, what are you bringing tomorrow so that we can find these centers? A compass. There are 4 centers that we're going to discover: the circumcenter, the incenter, the centroid, and the ortho center. And I think the way they do these pictures, this is very common in the textbooks. I think it's a very confusing way they do this. Would you say that the line from B through M to Z is a straight line?
No.
It isn't. But if you look from A to M to Y, doesn't that look like a straight line?
Kinda.
Yeah, so that's confusing. They're not supposed to be straight lines. What these are supposed to say is that the point at which 3 perpendicular bisectors intersect a triangle. So can we agree that MY goes through a midpoint and is perpendicular? So that represents a perpendicular bisector. They didn't continue it all the way up, but that's because it doesn't have to go through the vertex. Is X also a midpoint such that XM is perpendicular bisector and ZM? So these parts are all creating this center point, which then begs the question, what's up with BM and KM and CM? Well, what they're suggesting is that all 3 of those are the same length, which means that if I were to draw a circle centered on that point, it would circumscribe the triangle, which is why it's called a circumcenter. Draw around the outside. So that's the center that is the center of a triangle through all 3 vertices. All 3 vertices are equidistant. There's also something called an incenter, the point at which 3 angle bisectors intersect in a triangle. So again, you can see here that these are angle bisectors. They meet there. That doesn't mean that these MY, for example, is part of that, because as you can see, this bends. Rather, it suggests that these 3 green distances are all the same. So the three incenters will produce a triangle that is a circle that is inscribed inside the triangle. In other words, it's the center of the triangle because it's equidistant from all three sides. Centroid, which is by far the coolest name, which three medians intersect a triangle. And this is the center of gravity. So when you're spinning those triangle plates at Pier 39 to make a couple bucks, this is where you would put your finger. And it's connecting all three midpoints. Notice there's midpoints. Straight through this time to a vertex. Midpoint to a vertex. Midpoint. I would agree. That's a center that makes sense. But let's say that you've got a triangular backyard and you want to put sprinklers at these corners. And you want to find the center point to run out the sprinkler heads so that they're the same distance. This is the way you would decide that, in fact, this is the best way to cover your garden. This is the center you'd want. Okay, Ortho Center is the last one. This comes from altitudes. I kind of agree that the Ortho Center is bogus. There's not much real life value to this one. It is part of something called a 9-point or an Euler circle, which is kind of, or an Euler line, which is kind of cool. But you got to be a math nerd to appreciate that. Okay. So again, today we're talking about types of segments cutting through circle that are, or triangles that are specific, leading to a discussion of centers of triangles that we'll talk about next class. That intro sets you up for today and tomorrow combined. Today, your homework is all about triangle midsegments. So a triangle midsegment is a segment connecting the blanks of two sides of a triangle. Good, midpoints. As an example, in this case, DE is a midsegment for this triangle. And if a segment joins the midpoints of two sides of a triangle, then this segment is parallel to the third side and half as long. We talked about the fact that because this produces 4 congruent triangles, these corresponding angles are congruent, forcing these lines to be parallel. And if these triangles are all the same size, then DE length is the same as this part, is the same as this part. So DE is 1/2 of AC. DE is 1/2 of AC. Or maybe we don't like fractions and we could say that AC is twice DE. And then the other relevant fact is that DE is parallel to AC. Within today's work, what you'll find is there's 3 lessons I need from you. The first is that the lines are parallel. So look at number 1 and identify all pairs of parallel segments. If I tell you that RS is one of them, RS is going to be parallel to what? Good, XW. And you'll have a chance to go through and identify those. If in fact those lines are parallel, I know this is going to feel like we're jumping around a little bit, but please go to the final page, 4th page. Look at number 11. If in fact, this is a mid-segment, and it is because it's constructed from midpoint of this side and midpoint of this side, then I know that this 118 angle and this angle marked as 5 are known as what kinds of angles? Same side interior. Here's the transversal. There's same side interior. So 5 and 18 have what relationship? Supplementary, which means the measure of angle 5 plus 118 equals 180. Huh. You mean what we've been learning is still applying and taking us deeper? It's crazy. You're right. This is all about the parallel lines unit, isn't it? So as I said, there's 3 skills you're getting out of today's work. One of the skills is that you've got parallel lines, and just like Donovan is suggesting, that's going to reference what we learned about parallel lines before. The second thing you're going to see is like problem number 7 here on the back page still. What's the relationship between A, B, and DE? They're parallel, true, because DE is a mid-segment, so it's going to be parallel to AB, but in the front, you remember we saw 2 things. Good. We could say that DE is equal to 1/2 of AB. But notice what that's going to mean. If we substitute now, we get 4x plus 1 equals 1/2 of 11x minus 25. When we take half of 11x, we're going to get 5.5x. That seems more complicated than we need. So what if we rewrote it as the other way? Said AB is twice DE. Says the same thing, but now my algebra is going to be easier. 11x minus 25 equals 2 times 4x plus 1. So 11x minus 25 equals 8x plus 2 minus 8x. Add 25. X equals 9. It actually asked us to find the length of DE. So that's going to be 4 times 9 plus 1. 4 times 9 is 36 plus 1. So DE is 37. Question? Kind of fast. Sorry about that. Get it copied down, see if you can figure it out. Any questions on number 7 and how we set these up? This is the second skill I expect of you. The first is to recognize that parallel lines is going to make those angles have a relationship. The second is the lengths are going to be in a ratio of 2 to 1. The third skill I expect you to get from this is what's represented in number 15. I see x's, so I have to set up an equation. How do I determine what that equation is? You guys agree that these 2 angles marked are same side interior angles? If these 2 lines are parallel, which is what's true if they're mid-segments. They're mid-segments because of midpoints. If mid-segment, then parallel. If parallel, then same side interiors are what? Good, supplementary. And if supplementary, then those 2 things add up to make 180. So let's put those in. X squared plus 30 plus 6x plus 38 equals 180. So far, we've applied the mid-segment idea. But right now you're faced with an algebra skill that may be a little rusty for you. What kind of equation is this? Yes. It graphs as a parabola if it had a y in it instead of just x's, but those are a specific type of equation. It's not a linear equation, it's a quadratic. Excellent. And you're right, parabolas are tightly associated with those. I'm going to combine my terms on the left side, x squared plus 6x plus 68 equals 180. The reason it's important that we recognize this as a quadratic relationship is because that impacts how we solve this. If this were a linear relationship, I'd move my 68 to the right, wouldn't I? I'd get all my x's on the left and my numbers or constants on the right. But this is quadratic. So that's not my goal here. I need to get it set equal to 0. So I'm going to subtract 180 from both sides. X squared plus 6x minus 112 equals 0. Now, why did I do that?
But I don't know, that's kind of strange.
Well, it is kind of strange, except that I've got this tool in my back pocket called the zero product property. Anyone remember that property?
No.
Okay, so here's the idea. I've got two numbers I'm thinking in my head. And I'm going to give you one hint about them. Their product is 0. Can you tell me about one of my numbers? One of them has to be 0. Like if I tell you their product is 36, there is literally an infinite number of choices. 36 times 1, 18 times 2, 12 times 3, 9 times 4, 72 times 1/2. Right? There's an infinite number of choices. But once I tell you that their product is 0, you know that one of them equals 0. It's the only way that can work. So I need to take this adding of terms, x squared plus 6x plus a negative 112 equals 0. And I need to turn them into these two things multiplied. So what I'm going to do is I'm going to take the x squared and leave it as it is. I'm going to take the negative 112, leave it as it is. And I'm going to split this 6x into two different things. I could do like 7x minus 1x. I could do 8x minus 2x. There's an infinite number of choices, but the trick is I need to pick them so that they multiply to make a negative 112. So over here, I'm going to use the little diamond. You guys remember this? I'm looking to multiply to make a negative 112, and at the same time add to make a plus 6. Well, again, there's infinite choices that will give me a plus 6. I could have a positive 7 and a negative 1, a positive 8 and a negative 2, a positive 9, negative 3. But there's fewer choices that multiply to make a negative 112. I could have 112 times 1. I could have 56 times 2. I could have 28 times 4. I could come up with a whole list of these. The fact that this is a negative 112, what does that tell me about these things?
One has to be negative.
Excellent. One's going to be negative and one's going to be positive. That's how they'll multiply to make a negative. If I need their sum, when one's positive, one's negative, to equal 6, then I'm going to need my bigger one to be positive and my littler one to be negative, so that when they add up, they make a positive number. These two are 111 apart. That's way too far apart. These two are 54 apart. That's closer, but it's still pretty far. These two are 24 apart. This is still an even number, so I'm going to pull a 2 out of here, making 14, and multiply that 2 over here and make negative 8. And doesn't that work? 14 times negative 8 makes negative 112. And if you add those two together, it makes a positive 6. So I'm going to write these as negative 14, excuse me, positive 14 and negative 8. In other words, instead of writing this as 6x, I'm going to split it up this way. I'm going to go plus 14x minus 8x. Now I'm going to use something called factor by grouping. I'm going to look at the first two terms. What's common to both of those? X. This one's got an X, it's X times X. This one's got an X, it's 14 times X. So I'm going to factor that out. And what I'm left with on the inside is X plus 14. And if I were to double check myself, I could distribute again. X times X is X squared. X times plus 14 is plus 14X. Now, I want to pull something out for this one as well. And it's a little bit harder to see what's in common to both of these. But remember that we've already split out the negative 112 and said that it's negative 8 times 14. So can we agree that I can factor a negative 8 out of this one and a negative 8 out of this one? So I'm going to write negative 8 on the outside here. Negative 8 times what gives me negative 8x? And negative 8 times what gives me negative 112? Plus 14. Now, this is the important step to recognize, and I just heard some light bulbs go off, which is super cool. You know how here we saw that there's an X in there and an X in there, and we pulled that out? Look at these two together as one term and these two together as one term. And do you see that they both have X plus 14 in them? So I can pull out that X plus 14. And what's left? X minus 8. And if I check myself, X minus 4, or excuse me, X plus 14 times X would give me this, X times X plus 14. And X plus 14 times negative 8 would give me negative 8 times X plus 14. But I've gotten it to my zero product property. If these two numbers multiply together to make 0, then either this one has to be 0 or this one has to be 0. If this one is equal to 0, subtract 14 and X equals negative 14. If this one is equal to 0, add 8 and I get X equals 8. So it looks like I've got two solutions. However, that's the algebra. We're not in algebra, we're in geometry. Would both of these solutions work for this problem?
No.
No.
Why not?
Because it's two different solutions.
If I put a negative 14 in for X up here, 6 times negative 14 would be negative 84 plus 38 would be negative 46. Does it make sense for an angle to be negative 46 degrees?
No.
No, I can't have negative angles. So even though the algebra says this is a solution, the geometry says that's an invalid solution. But if I take X equals 8 and I put it in up here, 6 times 8 is 48 plus 38 is 70, 86. And X squared plus 30 is 64 plus 30 is 94. And do those two add up to 180 as I originally hoped?
Yep.
They do. So this is a valid solution. The problem asked me to find RTV. So I'd say the measure of angle RTV is equal to 8 squared plus 30, which is 64, plus 30, which is 94.
Are there more questions like this on the worksheet?
Again, in this homework, I'm asking you to learn 3 things. The primary is what comes from midsegments, so that the parallel lines make corresponding angles congruent. The second is that the segments are 1/2 to 1 or 2 to 1 relationship. And the third is a little reminder of quadratics. There's exactly one other question that has quadratics on it. The rest is focused on those other 2 concepts. You have the rest of the period to work on these. Please get to it.